All right, ladies and gentlemen, if you want to twist timing in your favor, then you can take LSD or you can listen to Lisa Thalheim. Sorry. A warm welcome, please.
Okay. Can you hear me? No. Okay. Nobody can hear me? Can you hear me now? Still? More volume, more volume. Thanks. Is that better? Who? Bar? Okay. Good afternoon. I'm going to talk about, well, the title is rather fancy, but it sounded better than talk on race conditions, but that's what the talk is about, race conditions. And I'm starting with a pretty picture from the 80s of a race condition, because it's one of my favorite movies. Other than that, it has no relevance to the talk whatsoever. I'd like to start with an I'd like to start with an opening note. I found just outside the knock, which greatly calmed me down. It says, you're welcome to present abstract concepts to us, which is what I'm going to do today. I don't really know much about practical exploitation of race conditions simply because I like to marvel at the shiny bugs I find and then get bored and move on. But there are people around who know about that, and you can make it your mission to track them down and ask them about actually tweaking load on a computer to get some obscure race condition exploit working. Okay, what I'm going to talk about is the mandatory intro. Then I'm going to introduce some common concurrency bugs, how to find and exploit them, and some not so common concurrency bugs, and close with some general advice when you're hunting for these kinds of bugs, and an end node. Okay, what are concurrency bugs? As the name suggests, it happens whenever there's multiple threads of execution happening, executing simultaneously, where threads, well, if you've done anything with threads, you're probably thinking about pthread, win32 threads, but I'm in general talking about any string of code being executed in parallel, which can also include processes. So, what are the basic requirements that you need before you can even start looking for race conditions in the first place? Is that you need multiple threads of execution. So there have to be either really simultaneous execution of multiple threads, meaning multi-CPU, or simulated simultaneous execution, as in what you usually have on a one processor desktop machine, where the threads get scheduled one after another, but from inside the threads it looks as though they're... Oh, okay. Better? Great. I hope I didn't lose you. Yeah. That's better. So I was rambling on about multiple threads of execution, which can mean threads as in pthreads or win32 threads, but also processes on different hosts. The next requirement is that they run simultaneously and share resources. So anyone who has brothers or sisters knows what I'm talking about when I use Lego bricks as scarce resources, or interact in any other way. For example, just communicate with one another using IPC mechanisms. So there's a whole host of concurrency bugs that can occur. Among them are deadlocks, live locks, mismatch communication, and false sharing, which I'm not going to talk about. It's simply because these are, first of all, quite rare to find in software because they're easy to find and easy to track down. If the software hangs, you can just attach a debugger and usually find out where exactly it hangs and what the bug is. And also, they're not very interesting for an attacker because usually when you hit a deadlock, that's basically the end of the line. So there's not much more in a deadlock than a denial of service, which is not all that interesting. Live locks and mismatch communication are the same. False sharing is just a performance issue. You can find more information on that in any operating system textbook. The interesting thing for an attacker are race conditions. So, what's the race condition? I think I'll start by showing an example. A really simple vanilla race condition, which may seem a bit cheesy because it's a constructed example, but I chose it for educational purposes. So, imagine you have a ring buffer sort of structure, and you have a store procedure, which always checks whether the limit of the ring buffer is reached, and if so, it just resets the ring buffer index to 0, and stores the data and increments the counter in a number of elements, which looks fair enough, I hope. So if you find mistakes in any of the code on the slides, that's very likely that there are actually mistakes. I tested the code, but you never know. So this code is okay in this setup. You have two threads, thread 1 and thread 2. And thread 1 comes in here, checks whether, so this in the middle column is the value of the RBF IDX counter. And imagine that it comes into this piece of code. The value of RBF IDX is 31. So it doesn't hit that piece of code, it just continues to write to the 31st cell of the ring buffer, increments it, at which point the index pointer becomes 32. And then the next thread comes in and sees that the RBF index pointer into the ring buffer is equal to cell, so it has reached its limit. So it resets the index pointer to 0 and continues from there. This is good. This is also still good. Thread 1 comes in as before, gets preempted at that point, meaning that it gets on a single core machine gets scheduled out and another thread gets scheduled in. And it sees that the RBF index counter has already hit the limit, resets it to 0, writes its data, everyone's happy. That at this point the structure is already inconsistent is a point, but never mind that now. So at this point the number of elements is not actually coherent anymore with a ring buffer. But it gets even more interesting if you have this kind of setup. The first thread comes in, checks whether the limit has been reached. Hasn't been reached, so this doesn't get executed. And at that point, it gets scheduled out for some reason. And another thread enters the same code, also sees that it still hasn't hit the limit, so this doesn't get executed, and stores its data into the 31st cell, increases the pointer to the next free cell, which is 32, which is beyond the limit, and at that point the thread 1 gets scheduled in again, gets to run again, and actually writes its data beyond the end of the buffer because the index pointer has been changed in between, but that thread has no means of knowing that. And it increases the index pointer once again, making 33, And because the programmer opted to check for equality here, this will never get hit again. It will just run away forever, or until it hits actually some crucial data of the process. So I showed that example because it's really easy to see how the order of execution of a series of statements can lead to a write beyond the buffer, which is a common concept in exploiting bugs. So that's just to set you up. And what we learned here is that the sequence in which code gets executed matters. And if you only have one thread of execution, it's given that code that is contained in the program serially will also get executed without interruption, without anybody altering the state of the world in between. But if you have multiple threads of execution that interfere or run in parallel, then you can have all kinds of, well, not quite foreseen events. And usually this results in data structures getting corrupted, which can, in this case, be used fairly straightforward to rank beyond the end of a buffer. So if another thread comes in here, index pointer 33, this doesn't get hit, just writes happily beyond the end of the buffer, increments yet again and again and again. So this was a constructed example. I didn't actually find that in any software. It was just for showing you what I'm on about. And here I'd like to say some things about why I like race conditions. Race conditions are really hard to find. If you ask programmers, they will also tell you that they hate race conditions because they have a habit of showing up every 1,000 iterations and then never again. And then you just get random weird bugs and don't know what actually happened. And also race conditions tend to manifest themselves not in the places they actually happened, but somewhere entirely else in the code. And tracking down race conditions is incredibly hard and can be incredibly hard, which is why even if the programmer hits a race condition in his testing and debugging, there's a good chance that he'll never get around to actually tracking it down or fixing it, because it takes so much time and deadlines pressing. And also I like them because they're fun puzzles. Race conditions tend to be very complex bugs, and you have to keep a lot of context in mind to twist it around. So it's an intellectually interesting puzzle. You may have guessed by now that I'm more of a just give me some puzzle, I don't care about the implications sort of type. Okay, there are, race conditions can come in all kinds and forms, and we're actually going to see some that don't really fit into any pattern, but there are certain patterns when talking about race conditions. The first one is the forgotten lock, then we got file system races and signal races, and I'm going to talk about each of these in turn and give examples of them. Well, not for the forgotten lock, because the forgotten lock is just either the programmer didn't think of synchronization at all, or they used it inconsequently, which sucks because you just have to miss out on synchronization in one place in the code. You may do perfectly in all of your code and miss just one spot and one access to some global shared data, and then you're screwed, because then there's a chance that the data structure gets corrupt. So that's very much in favor of an attacker, because the programmer has to be perfect, and the attacker just has to find the one famous inconsequent use. And I'm thinking about whether I'm talking about that later. I might as well just do it now. You might think that synchronization is not that hard. You just put a lock around the data you're going to access, But in real-world code, you usually have several levels of function calls, and if you don't make any very explicit assumption and advice for fellow programmers on who has the responsibility of locking a data structure, you might end up with code paths where no one locks the data. So there may be some code paths where somebody thought of locking it, and then there may be 10 calls one after another, and nobody feels responsible for actually locking the data structure because nobody declared at which point it's supposed to be locked. And this is something I've seen quite frequently in industrial code, that there's just so many levels of indirection that the programmer loses track of where they have to lock the data and where the lock is already held. So this basically just this ends up being a vanilla race condition. So it's pretty much as though you don't have any synchronization at all. So finding it is a bit of a hassle. You actually have to check every access to a shared data structure or a shared resource to make sure that it's properly locked in that place. And there's, well, the term acquiring a lock is often used in code, but the problem is that in most implementations, nobody actually acquires anything. So there's no field in the thread or whoever acquires the lock that says, I have the lock. It just gets acquired by someone. And it's really rather hard to just take a snapshot of a system and say who has the lock. And yeah, I already mentioned that before. If you see that there are several call layers involved, be very careful, be extra careful, because probably the programmer made a mistake just because the software is so complex. And even more so if it's not a single author but multiple authors, as usually is the case in industrial software. So that sounds very general, but there's not really much more to help you with finding a forgotten lock. And something to also look out for is shared resources or data that are not actually explicitly shared, but implicitly. I'm going to talk about that later. So, which is a very nice bridge to the file system race, because the file system race, if you think about it, it's actually just one giant shared resource for processes on a system. And if you don't think about it properly, you might just forget to lock access to that giant shared resource, which happens quite frequently still. Even though file system races have been described years and years and years ago, there's a paper from 1995 by Matt Bishop detailing that, and still there's file system races. And here's an example I found on the internet. I think it's from a 2001 version of software, where you can actually get code execution by exploiting a file system race. So what you have is temporary directory. There's something to look out for. Temporary directories are quite frequently messed up. So if you see some code handling temporary directories, look out. Also, what you immediately see, this is not C. So maybe somebody has got the impression by now that race conditions are only a problem for C code, which is not the case. This is Perl. So it makes up some name for a temporary directory and then checks whether this directory exists. And if it exists, it just deletes the directory. Then checks whether it exists as a file, and if it exists, it unlinks that file, and then creates that directory with appropriate access rights. Now the problem is that in this phase marked red, nobody keeps you from just, after the code has passed through this check and possibly deleted any old temporary directory, just create a new one. If you create a new one and quickly put some kind of file in there, this may succeed, but this will fail. Unlink fails if the directory is not empty, but the return code is not checked, so nobody cares. And also with the mkdir, this one will just silently fail, but the return code is not checked, so nobody ever knows that there was already a directory there. So then you own that temporary directory, which this script is going to write to with its own exercise rights, obviously. On what people then actually did, another part in that logwatch tool, which is what we just saw the code of, is to make up a command line and then execute that command line. And you see that there's content piped into another file here. And the command becomes something like just get the contents of that log file, pipe it into a script from logwatch. It just filters out all the relevant entries by date. So if you declare that the logwatch is to look at log entries from yesterday, then it just filters out all the log entries from yesterday and outputs this into its temporary directory, which, remember, we now own. So nobody keeps us from setting symbolic links there, right? We own it. We can do anything in that directory that we please. And so what if you, Brad, I messed up. This is still supposed to be secure, and this is also still supposed to be secure. So what if you link that file to, say, root bash rc, something that gets executed frequently with sufficient privileges? This is, of course, assuming that logwatch runs as root 2, because otherwise it couldn't write to that also. So what happens? The log messages from that log file get written into root bash rc. So all you have left to do is just get something logged that's actually a valid shell command. Like that. You can try to execute such a log file. It will do exactly that. And this will get done with the privileges that bash rc is run with. So this is a delayed access. The first time that logwatch runs, it writes to that bash rc, and the next time that somebody runs bash rc, you can write to etc/pd, which sucks. So that was one example of a file race. And the problem here was that, number one, return codes weren't checked, which is always a bad idea, but usually people just say, oh well, it doesn't matter. There's no way you can exploit it, which is a common theme, because race conditions are so complicated that you can often use dormant flaws in the software that nobody really cares about until the state of the program gets unstable, which is exactly what race conditions do. And the other thing is that you cannot assume that the file access calls that actually take path instead of file handles are atomic. Anything can happen in between two calls to functions that take path. And there's a common term in the literature, which is time of check versus time of use. It gets checked here, then anything can happen, because there may be other processes, other threads running concurrently. And time of use, the state of the world may already be completely different. Oh, bad luck. But it might already have helped to just check the return value of that. As I already mentioned, temp file handling is usually a good place to look. So if you see any code in any language handling temp files, look at it. And what the Bishop paper actually suggested was to look for sequences of file operations that accept parsers arguments like, I don't know, in Perl it will be open or mkdir. And also if you're a programmer, it's interesting to know that for almost all the file system functions, there's an equivalent that operates on file handles. So you open the file once and then you're bound to one file handle, and what happens in between doesn't concern you that much. It's not that it doesn't concern you at all, but at least certain operations can be seen as atomic then. So use them if possible, if writing software. Something that's a little more complicated, and I tried to figure out how to present this here, but I decided that it couldn't be presented on that small little screen, are signal races. I can just explain the basic principle to you, and then there's an excellent paper by Mikhail Zalewski, which details everything, basically everything you need to know. So if you're interested, just find that paper. But the basic principle is that calls to non-reentrant functions are made from signal handlers, and signal handlers can get called at basically any time during your program runs, even while the code is in a signal handler. Examples for such non-reentrant functions are the ubiquitous malloc or free or syslog. So what's quite commonly found is signal handlers for sigquit, which try to write some log message to syslog, but that function is not reentrant. So something that's also commonly used for similar signals is the reuse of signal handlers. So you write one function and use it as a signal handler for both sigquit and sigkill. And without ever thinking about making the signal handlers themselves reentrant. So in that case, all kinds of bad things will happen, but it will be apparent that just entering malloc, having malloc get interrupted at some basic point while modifying heap structures, and then entering malloc again and using that heap structure that was just corrupted is a really bad thing to happen. And one example of a signal race, a really simple one, is by a brilliant multi-threaded HTTP called MyServer. It's a very good lecture on how not to write multi-threaded code, incidentally, if anybody cares to learn how not to do it. And they also, like I just said, they define one function, use it for two signals, sigint and sigterm, and call two functions here. Well, sync is well. I concentrated on the my server code. Stop is actually okay. It's just setting one variable, which is actually the recommended thing for a signal handler to do. Just set a variable and have the program handle the next time it gets into a loop. But server log write line does something like that. That's log write line. It's pretty long. It calls some other function, which is also quite long. And this calls yet another function, which I couldn't even fit on the slide anymore. And somewhere inside that function, incidentally, buffers get assigned by new, and buffers get freed, and so you have calls to memory management functions, which I just said is a very, very bad idea. So that's a picture book example of multiple levels of indirection and screwing up your multi-threaded code. Well, no, that's not actually about multi-threading. That can happen if you don't use multi-threading at all. It's a process thing. Okay, the signal race is a bit harder to exploit, but it's quite easy to find. You just look for the calls to sig actions, see which function pointers are passed to it, and then see what these functions do. It's that straightforward. Then there was a funny bug in GCC before version 4. Favour already mentioned that in his talk. But GCC, the C++ compiler of GCC before version 4, managed to always generate code that contained a race condition. So the programmer didn't have to do anything wrong at all, and still there would be a race condition, and you couldn't see it from the C code. So what this says is this is a local static. This gets initialized exactly once the first time that somebody calls this function. And GCC generates code from this like that. It introduces an extra variable, a helper variable, a kind of flag that says, yeah, it has been initialized, don't bother to do it again. And it loads the helper, tests it here. Then here's the initialization. Well, the call that retrieves the value for the initialization. The value gets written to a static local variable. Then you load the helper again from memory and lock down that helper by just setting the flag. So here's what may happen. There may be two threads accessing this function for the first time simultaneously, albeit a bit with a bit of delay. So the first one reads from memory that flag helper variable, sees that it isn't set, gets past this test, everything's fine. Actually gets around to initializing our local static variable, but the helper variable is still 0 because it hasn't been updated. So at this point, the second thread comes in, gets scheduled in for whatever reason the scheduler decided to move it in. But that's the thing, you always, if you're writing multi-threaded code, always assume that your code can get interrupted at any point in time. So it also retrieves the value of the flag from the memory, sees, well, it may get scheduled out at that point, it may not, doesn't really matter. Eventually, the first thread will get around to setting the flag and leaving, but at this point, the second thread has already retrieved the value from memory and uses it and gets past the test, even though the variable has already been initialized once, and it initializes it again, which really sucks because local static means that it gets initialized exactly one, and the programmer is supposed to be able to rely on that. And the reason that got fixed in CC4 is that somebody actually filed a bug where the local static int was an object, and this way of generating codes ended up calling both the constructor and the destructor twice. Not good. So don't do that. And here's a thing again. With race conditions and with concurrent execution, all kinds of things that you take for granted can suddenly happen, unless you guard against it properly. Which, well, I don't want to bash programmers because it's really hard to get synchronization right. And if you told me to write a multi-threaded something right now, I'd probably make a million mistakes and introduce dozens of race conditions too. So. More education examples. That doesn't actually fit into any of the 3 common categories I gave you. So if you're looking for race conditions, don't limit yourself to looking for these patterns, but be open-minded and always think about what would happen if the code got interrupted at this point. And this is an example from that libc. This is not to piss off Favour, it's because he challenged me once, and it's not even it's not even triggerable in the current code base, so don't bother. But it was a neat bug, and it was rather educational. That's why I put it here. It's the syslog code, appropriately put into the directory libugly, and this is a global variable which holds the log tag. It's 1,000 chars long. And you first have to call openlock, and what openlock does is, if it finds an identifier, it copies it to log tag for later use, which is global. So any number of threads that run concurrently can write to this. Writing at max log tag chars, which is fine, and then no terminating it, which is fine. But what if the code gets interrupted at this point, right after string strn copy? The identifier might be just 1,000 chars long, so it gets copied all the way into a 1,000 char buffer. So at this point, you have a runaway buffer, and depending on what's after that, you have an arbitrarily long string. This will end up in the BSS section of a binary, and anything that's a global uninitialized variable will end up there, so there's a good chance that there's something behind it. Especially it's aligned to 4 bytes, so it may happen that after that there's more data. And then you have, in the actual syslog call, you have this code. You have a buffer of buff size, which is 2048, and then you retrieve the header len by writing to that buffer a string, which also gets influenced by log tag. And the funny thing again is that the semantics of snprintf, you think that's safe because it's snprintf and it says to only write 130 units to the buffer, which it does. But what snprintf does is, if the string is actually longer than the buffer, it returns this number to the caller. So header len make it larger than 130. And this is something that the code doesn't take into account, and it uses header len later to compute an offset into the buffer and give a number of bytes to write to that buffer. So this can get very large. It writes beyond the buffer, even though you thought you were safe, and all only because the code can get interrupted here, which it can actually not, because every call to that syslog function is protected by a mutex, but still it's educational. And just to see how seemingly innocent and correct code constructs can have disastrous effects. Then there's the bizarre race conditions, where you sit in front of your computer, look at your editor and think, what the hell was the author thinking? This is one example. I have to give a bit of context here. It's, again, from my server. It's contained in the method server terminate, which is not a deconstructor, which is important for the bug to be interesting. It locks that structure, so it can access it, which it does, and then unlocks it, and then it deletes the mutex. So it frees the memory where the mutex resists, which is just plain stupid, because either you assume that the that this data structure can get accessed by several threads at a time, then you have to assume that they all use the mutex, because if one doesn't, then you're screwed. And if you assume that at the same time some other thread may access the mutex, it's a really bad idea to just delete it in the middle of it. And I tried to track that, and I think it might actually be exploitable, because the only thread that can make threads mutex get executed are contained in this data structure, and they're cleared here, but they're created using new, which means they're residing on the heap, and clear doesn't guarantee that the memory gets freed though. So it's still there, and they may still be running. So if any of you is bored, they can just find my server on the internet and see whether they can actually exploit this bug. And there's even more in there. Even the mutex objects in that code have race conditions. That's really a stunt. Okay, let's come to some really, really high-level general advice on finding RCs. Look out for resources that are not obviously shared. So the programmer may not be aware that they need to log. If they have some, I mean, if they think about the design of their multi-threaded program and say, okay, I need this global variable to be shared among the threads, it's likely that they're thinking about synchronization. But there's quite a lot of libc function calls still that use static variables internally, like syslog, like the famous string search functions. And the programmer may just not be aware of that. So look out for these function calls and just think hard every time you read code about which resources the code uses that may not look shared, but they are. This also applies to, I don't know, devices, shared memory sections, stuff like that. One other thing I found useful is to look out for constructs that indicate that you're dealing with a singleton object, which is a well-known pattern from object-oriented programming. And it basically makes the object itself into a global kind of variable because it gets initialized once and then every time somebody accesses it, it just returns the same instance. So every time you see something like instance of getting called, make a mental note that this is actually a global shared data structure, quite likely. And a closing word, because my friends from Dylan like to point out that they're safe because there are no buffer overflows in Dylan. I think by now they did away with that delusion. But it's the same with race conditions. Do not assume either when writing or auditing code that the software is safe just because it's not multi-threaded. As I said, there's race conditions that occur just with processes involved. And don't think you're safe just because it's not written in C and C++. While you can make huge mistakes in C and C++, as we've seen even also Perl and almost just pretty much any language can introduce race conditions, and even the famous Erlang, which I'm personally very fond of, is not safe because it may not have shared data, but there's still the possibility of logic faults being introduced by race conditions. So look out for all of them. They're out to get you. That's it.